Welcome to a journey into one of mathematics' most fascinating paradoxes. Today, we're exploring the Möbius strip, a seemingly simple shape that defies our intuition about how surfaces and edges should behave. Named after German mathematician August Ferdinand Möbius in 1858, this remarkable geometric curiosity continues to influence science, art, and technology to this day. Join us as we unravel the mysteries of this one-sided wonder and discover how a simple twist transforms an ordinary strip into something extraordinary. The Möbius strip stands as one of geometry's most elegant puzzles. At first glance, it appears to be just a loop of paper with a twist. But this shape challenges our fundamental understanding of surfaces and dimensions. What makes it truly remarkable is its possession of only one side and one edge, despite being constructed from an ordinary strip of material. Unlike a regular loop which has an inside and outside surface, the Möbius strip seamlessly blends what should be separate sides into a continuous surface. This property has fascinated mathematicians since its discovery, and continues to inspire scientific inquiry across multiple disciplines. Creating a Möbius strip is surprisingly simple, yet the result is profoundly complex. To make one yourself, start with a rectangular strip of paper about an inch wide and several inches long. Hold the strip at both ends, then give one end a half twist, rotating it 180 degrees. Now connect the ends together, forming a loop with that crucial twist. What you've created isn't just any loop, it's a topological marvel. The process transforms an ordinary two-sided object into something with just one continuous surface. This simple construction opens the door to exploring the strip's counterintuitive properties, allowing anyone to hold a mathematical paradox in their hands and experience its strange behavior firsthand. The most famous property of the Möbius strip is that it has only one side, defying our everyday experience with objects. To demonstrate this remarkable feature, imagine taking a pen and placing it on what appears to be the outside surface of the strip. Begin drawing a line down the middle, continuing without lifting the pen. As you trace along, something astonishing happens. Your line eventually returns to the starting point, having covered what seems to be both the inside and outside of the strip, without ever crossing an edge. This experiment proves that the distinction between inside and outside doesn't exist on a Möbius strip. There is only one continuous surface. In traditional geometry, objects like paper sheets have distinct front and back sides. But the Möbius strip transcends this limitation through its unique topology. Equally fascinating is the Möbius strip's single-edge property. If you place your finger on any point of what appears to be the edge, and trace along it continuously, you'll eventually return to your starting point, having traveled the entire boundary without encountering another edge. Most objects we interact with daily have multiple edges. A sheet of paper has 4, a ring has 2, inner and outer. Yet the Möbius strip, despite its three-dimensional presence, contains just one continuous boundary. This property further cements the Möbius strip as a topological anomaly. The single edge challenges our spatial intuition and demonstrates how a simple twist can fundamentally alter an object's geometric properties. In the field of topology, the Möbius strip holds special significance as an exemplar of non-orientable surfaces. Topology studies properties of space that remain unchanged under continuous deformations, like stretching or bending, but not tearing or gluing. The Möbius strip demonstrates how a simple twist can create a fundamentally different topological structure. Mathematicians classify it as a non-orientable surface because it's impossible to consistently define an up direction across the entire surface. This property connects to more complex topological concepts like the Klein bottle and projective plane. The strip serves as an accessible entry point to understanding these abstract mathematical ideas, providing a tangible example of how topology can reveal surprising properties in seemingly simple objects. When you cut a Möbius strip, the results defy intuition in fascinating ways. Cut a normal loop down the middle, and you get two separate loops. But cut a Möbius strip lengthwise down the center, and instead of falling apart into two pieces, it remains intact as one long loop with two full twists. No longer a Möbius strip, but a regular band with twice the original length and half the width. Even more surprisingly, if you cut the original Möbius strip a third of the way from the edge, you don't get two separate bands, you get two interlocking bands, one a Möbius strip, and the other a regular band with two twists. These cutting experiments reveal the strip's remarkable topological properties and demonstrate how its single-sided nature leads to counterintuitive outcomes that continue to fascinate mathematicians and puzzle enthusiasts alike. The Möbius strip has transcended pure mathematics to find practical applications across numerous fields. In engineering, conveyor belts designed as Möbius strips wear evenly on both sides, despite having only one surface, effectively doubling their lifespan. The electronics industry has utilized Möbius-inspired designs in resistors that cancel their own self-inductance. Perhaps most famously, the recycling symbol with its three arrows forming a triangular Möbius-like loop represents the continuous cycle of materials being reused and repurposed. In computing, Möbius principles have informed the design of non-volatile memory devices. These practical applications demonstrate how a seemingly abstract mathematical concept can solve real-world problems through its unique properties, proving that theoretical mathematics often finds unexpected utility in industry and technology. The Möbius strip has captivated artists, writers, and cultural figures with its paradoxical nature and symbolic potential. Usher, the Dutch graphic artist, incorporated the Möbius strip in his famous work, Möbius Strip 2, depicting ants crawling along a single-sided surface in an endless journey. In literature, the strip represents infinity and cyclical narrative structures, appearing in stories that loop back to their beginnings. Sculptors have created monumental Möbius installations in public spaces, inviting viewers to contemplate infinity and continuity. Musicians have composed pieces inspired by its continuous form, and filmmakers have used it as a metaphor for time loops or paradoxes. The strip's elegant simplicity, combined with its profound implications, has made it a powerful symbol across creative disciplines, representing everything from eternal return to the interconnectedness of opposing concepts. Beyond mathematics, the Möbius strip continues to influence cutting-edge scientific research. In molecular biology, scientists have discovered Möbius-like structures in certain DNA configurations, where the genetic material twists in ways resembling the famous strip. Physicists studying quantum mechanics have found the strip's topology useful for understanding certain particle behaviors and quantum states. In materials science, researchers are developing Möbius-inspired structures with unique electromagnetic properties that could revolutionize communication technologies. The concept has even extended to cosmology, where some theoretical models propose Möbius-like configurations of space-time itself. These applications demonstrate how the strip's fundamental properties, its one-sidedness and single boundary, continue to provide valuable frameworks for understanding complex phenomena across scientific disciplines. The Möbius strip fundamentally challenges our intuitive understanding of dimensions and space. While we typically think of objects as having clear distinctions between inside and outside, top and bottom, the Möbius strip blurs these boundaries in ways that hint at higher dimensional geometry. It serves as a gateway to understanding more complex topological objects like the Klein bottle, which has no inside or outside, and cannot be properly represented in three-dimensional space without self-intersection. These shapes prompt us to reconsider our assumptions about spatial relationships and boundaries. Mathematicians and theoretical physicists use these concepts when exploring higher dimensional spaces and the fundamental nature of our universe. The Möbius strip thus becomes not just a mathematical curiosity, but a conceptual tool for expanding our dimensional thinking beyond everyday experience. What makes the Möbius strip so powerful is its ability to make abstract mathematical concepts tangible and accessible. With just a strip of paper and a half-twist, anyone can hold a topological paradox in their hands, experiencing directly what would otherwise remain in the realm of abstract mathematics. This physical demonstration bridges the gap between theoretical concepts and sensory experience, allowing us to literally touch a mathematical truth. The strip teaches us that surfaces and boundaries are not always what they seem, revealing that our intuitive understanding of space often falls short of reality's complexity. As a teaching tool, the Möbius strip has introduced countless students to the wonders of topology, serving as a gateway to more advanced mathematical exploration. Its simplicity belies its profound implications, making complex topological ideas accessible through direct physical interaction. The Möbius strip represents one of mathematics' most elegant paradoxes, a shape that transforms our understanding of surfaces, edges, and dimensions through a simple half-twist. From its humble origins in 19th-century geometry to its modern applications across science, art, and industry, this remarkable structure continues to challenge our perception of reality. The strip's ability to exist with just one side and one edge serves as a powerful reminder that the universe often operates in ways that transcend our everyday intuition. As we've seen throughout this exploration, the Möbius strip is far more than a mathematical curiosity. It's a gateway to understanding topology, a source of practical innovation, an inspiration for artistic expression, and a conceptual tool for expanding our dimensional thinking. Whether you're a mathematician probing the depths of topology, or simply fascinated by this twisted loop of paper, the Möbius strip invites us all to reconsider what we know about the nature of space, surfaces, and boundaries. In its elegant simplicity lies a profound truth. Sometimes the most fundamental aspects of reality are the ones that surprise us most. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.